Hello everyone, I am Tarika Ramesh Kumar, Graduate Research Assistant at the Advanced Propulsion Research Laboratory at Open University. This presentation is a part of my doctoral research, and it is about how to analyze stability of internal flows in rocket motors, meaning in porous cylindrical chambers. So these are the challenge questions that were given to me. So to provide a concise but self-contained exposition of the experimental, analytical, and numerical techniques used to analyze the stability of internal flows, as well as the most recent developments in the field. Could any of these tools be used at the basis for constructing a cost-effective and generalized numerical stability framework that can provide insights on the stability inside a motor? And can this framework be validated using experimental studies by the French aerospace lab ONIRA? So here is an outline of my presentation. First, a brief introduction to combustion and stability in rocket motors, with how both acoustics and aerodynamics play a very important role in it. Next, we'll look at how the stability of flows is analyzed over the years and the various methods that are available in the literature to do that, followed by the important milestones in stability analysis and a summary. Before we get into the how, let's take a look at why the study is significant in the space race. So Stephen Hawking, the best known theoretical physicist of our time, encouraged us to look up at the stars and be curious about how the universe exists, as it is a key to our civilization and existence. Space travel for everyone is not very far in the future, and we are looking at potential moon and Mars colonization in the next few years. Though the US space program's ambitions are higher than ever before, NASA currently receives only 0.4% of the federal budget as compared to the 4% during the Apollo program. We need more powerful engines, but the complex nature of flow physics hinders the process, and one of the most important problems encountered is combustion instability. Inside a rocket motor is a high energy environment with typical chamber pressures reaching about 20 megapascals and temperatures of about 3000 degrees Celsius. As we know, idle flow does not exist in nature. There will be perturbations that will result in oscillatory flow. Combustion instability is a phenomenon which occurs when the oscillations associated with the high energy levels of the motor grow to very large amplitudes and affect the structural integrity of the motor. These instabilities are capable of destructing combustion chambers in fraction of seconds. Typically, this failure occurs due to thermal overload, due to drastically increased heat transfer and also a disturbed combustion zone. Even if the oscillation amplitudes are smaller and can be contained, it can have adverse impacts such as vehicle vibrations, destructive overpressure, elevated heat transfer, and mechanical loads on internal components. And sometimes the unexpected force and torques can also degrade the system performance. So here are videos of static testing of solid rocket motors, one experiencing a stable burn and another experiencing an unstable burn. You can see that the stable motor is burning with a nice cone-shaped exhaust plume, but the unstable motor's exhaust plume is experiencing oscillations in the direction of the velocity vector. And this will result in pogo oscillations, and this is what destroyed the Apollo 6 mission. And these low frequency oscillations are termed as chugging, and they have a frequency of less than 150 hertz generally. So intermediate frequency oscillations are termed as buzzing, and high frequency oscillations are called screeching, and they are named based on how they are perceived by humans. The upcoming SLS mission to Mars uses the RS-25 and RL-10 engines that are about 47-year-old with a few upgrades. In history, combustion instability has been the cause of cancellation of many programs and also the delay of the moon mission due to it being a very costly problem. The most prominent example of an engine suffering from combustion instability is the Rocketdyne F1 engine used in the Apollo mission, which took more than 1,300 full-scale tests until a stable configuration was achieved. This is one of the major reasons that keeps engineers from designing more powerful engines. Similarly, the Space Shuttle solid rocket boosters exhibited pressure oscillations at 10 hertz, which is exactly the first longitudinal acoustic mode of the motor, showcasing that this is an acoustic problem. To provide a better explanation, let's consider a guitar. An acoustic guitar is actually just like a rocket, an air chamber with strings tuned to different frequencies. Let's say you pluck the D string. The sound is produced because the body of the guitar vibrates in the same frequency of the string, and this is termed as resonance. The lowest frequency is called the first harmonica mode, and the next resonant frequency, second mode, and so on. The mode number governs the loudness and shrillness of the sound. Now, this produces a pleasant melody in the case of a guitar, but if the same thing happens in a rocket, this will be disastrous. The guitar strings are analogous to the fluid motion in a rocket, and the guitar body is analogous to the rocket chamber. Now, let's take a look at evidence of this in the literature. The figure on the left shows a waterfall plot of the instabilities during a firing of a full-scale Titan 34D motor. Currently, Raytheon, but at that time, United Technologies, Brown and his team reported pressure oscillations of the full-scale Titan 34D at approximately 2% of the mean pressure. Now, the frequency of these oscillations, as you can see from the solid lines, match the 1L and 2L modes, which are about 23 hertz and 47 hertz respectively, and that is a recipe for disastrous. At about 45 seconds, they start matching the 1L and 2L modes. So this is when the resonance occurs. On the right, we have the waterfall plot of the space shuttle redesigned solid rocket motor reported by Mason and researchers at ATK Tehkol, currently with Northrop Grumman. As you can see here, the first mode frequency is about 14 hertz. It turns out that this frequency is very close to human brain's reaction time to external stimuli. There was some worry by NASA that the booster oscillations might interfere with the astronauts' ability to control the vehicle. Fortunately, this was not the case, although astronauts were warned about feeling the vibrations during booster operation. So even if these issues, even if the frequencies don't result in combustion instability, it is important to have a knowledge of the modal frequencies of any flow to avoid any issues. Unlike the space shuttle, the Ares 1 vehicle had structural harmonics near the frequencies created by the motor. This caused the structure to resonate and impose large acceleration on the rocket, large enough that the astronauts' lives and integrity of the rocket itself may be endangered. Now, the test flight also showed damage to the booster. The oscillation problem of the Ares 1 vehicle could not be solved, and it finally led to the cancellation of the program at a very advanced stage. So here, in a closed boundary condition, a pressure wave gets reflected, mimicking a feedback amplifier, as graphically shown here. Here is a video which shows this phenomenon in a tunnel where we can actually physically see the pressure wave traveling back and forth because of condensation of water vapor in the air until the pressure returns to normal. You can see that the pressure waves, the oscillating pressure wave actually dies down in here, but when a combustion instability occurs, these oscillations actually keep growing and growing, and that is what results in destruction. Now, moving on to hydrodynamic instabilities. Instabilities can occur anywhere, in solids, control systems, fluids, including liquids, gases and plasmas, interstellar systems, etc. We are only concerned about the fluids here. Real flows are subjected to disturbances of various types, and they distort the existing force equilibrium. In a stable flow, the disturbance will gradually die down, but in an unstable flow, the disturbance will continue to grow, as illustrated in this slide here. Applied mathematicians and mathematical physicists like Helmholtz, Kelvin, Rayleigh, Bohr, and others are the ones who pioneered the hydrodynamic instability. Looking at the Reynolds pipe flow illustration in here and smoke from a cigarette, we can easily identify laminar and transition to turbulence and turbulent regimes. Now, here is a picture of the DNS of a Rayleigh-Taylor instability when a heavy fluid is set above a lighter fluid in the presence of gravity. The heavy fluid penetrates and which are denoted by the spikes, and the lighter fluids, which are like the bubbles over here, creating a mixing zone. As the spikes and bubbles evolve, turbulence is formed within the mixing zone, which is a signature characteristic of the related line stability. Now, similarly, based on the pattern observed, like the spikes and bubbles in here, the instabilities are named as Kelvin-Helmholtz instability, Tolman-Schlichting instability, Gortler instabilities, to name a few. Now, transition to turbulence occurs due to the onset of coherent structures. These coherent structures in fluid flow are still beyond our current understanding. Here, in connection with rocket motors, this is actually an inherent instability of the mean flow. Numerous cold flow experiments designed to understand the hydrodynamics of the flow, they actually exhibited definite frequencies, just like we saw before in the acoustic instability. Now, let's look at the waterfall plot of the Minuteman 3 here. Here, you can see that the same situation is observed. So the solid line denotes the 1L mode, but in addition to this, the observed frequencies matching the 1L mode, with passage of time, the frequency is lowered, and this is something which the scientists termed as the locking-in phenomena. The characteristic frequencies make sudden shifts with time, and this indicates vortex shedding as a major source of driving energy. So when dealing with nonlinear combustion instability prediction, it is important that vortex shedding and its coupling with acoustics is considered as a mechanism. And since linear stability analysis serves as a precursor for the nonlinear combustion stability prediction, we need to consider this vortex shedding phenomenon too. That is why it is important to model or analyze or design a solver that considers the pressure velocity coupling in here. Now, turbulence starts with vortex shedding, and we can identify 3 sources of it in a rocket motor. Any protrusion in the flow can cause obstacle vortex shedding, and vortices generated by the sidewall is the pyramidal vortex shedding, which is actually an intrinsic instability of the mean flow, and the backward facing stack at the end causes angle vortex shedding. Now, a sure shot, accurate prediction for practical applications are not workable up to now. The physical mechanism itself from which these oscillations originate is still not well understood. So we have different methods that provide insights on different aspects of the flow. Experiments with combustion are obviously more realistic, particularly concerning ambient conditions, such as the pressure, temperature, the combustion process, and also the slow increase of the cavity volume to the wall regression. But measurements are actually not easy in such conditions, and only global information becomes available. Conversely, setups using gas at ambient condition, which are like the cold gas experiments, they allow inflow detailed measurement in addition to the ones similar to those used in combustion. Next, we know that numbers don't lie. So analytical methods, though under many assumptions and ideal conditions, serve as a basis for theoretical knowledge, specifically to determine the correct boundary conditions and to validate the computational methodology. Considering the numerical methods, we have the larger D simulation, where small turbulence scale is filtered, but all the rest is resolved, like the flow, acoustics, and also the species by brute force. RANS solvers, they allow parametric studies, DNS and DES, and the computationally solving the linearized Navier-Stokes equations where mean flow is frozen. These are some of the popular techniques. And for my research, I am using the linearized Navier-Stokes equations to get an idea about the stability. Now, experimental techniques over the years have been with full-scale and reduced-scale firings and cold gas setups. The results from them have provided evidence for the definite frequency signature, as showcased in the frequency plot over here. As you can see, the dotted lines, they are the acoustic modes, and the results from the LP9 subscale motor, the frequencies actually match the acoustic modes of the motor. Some of the other experimental facilities around the world, we have the pressure oscillation demonstrator, which was used to simulate the instability of combustion inside a solid rocket motor. The issue under test was the frequency of thrust oscillations coincident with the acoustic modes of the motor cavity, specifically focused on the Aries 1 problem. Next, we have the French aerospace agency ONIRA had two cold flow experimental setups. One is VECLA and one is Waldo, which are the channel and cylindrical flow setups respectively. And the rocket engine test bench at Kessler is a subscale test facility with piezoelectric pressure and acceleration sensors. At Purdue University, there is the CVRC, continuously variable resonance chamber. It is also a reduced scale setup capable of varying the length of the oxidizer post by moving the location of the choked inlet in the oxidizer tube. Now, this in turn enables the tuning of the instability modes in the combustor, and it is also aimed at testing the effect of different fuel types. Now, a little bit more about the Waldo cold flow setup. It is a 1/30th scale modular axisymmetric test facility with 4 segments of 60 millimeter internal diameter. Each segment has a length of about 168 millimeters. Now, a removable CD nozzle with a throat diameter of about 28 millimeter is also available for some studies. Pressure transducers and thermal probes are installed at different locations on the setup and at the closed upstream end on the injecting module. Now, this was actually used to analyze the Ariane 5 segmented solid motors. Some of the information was kept confidential. That's why it was, some of the publications had some segments in there, but then it was revealed that it was a 4-segment motor. So similarly, a 4-segment setup. Now, some of the results, as the chamber length increases, the fluctuation amplitude also increases. As you can see, the measurements at different locations is shown here, and especially at the longer length of the motor, the amplitude is very high. And you can also observe 3 distinct peaks on the velocity spectra from the frequencies 170 Hertz, 320 Hertz, and 500 Hertz. So this simulating the same conditions in our stability solver will allow us to actually validate our solver. So the spectra on the right, it is clear with all the necessary information, and this will serve as the experimental validation for any computational stability framework, especially mine. So there have been multiple analytical approaches to the flow stability problem, beginning from Rayleigh criterion. Since the instabilities were classified based on noise initially, Lighthill put forth an acoustic analogy approach, followed by studies based on wave equation, asymptotic mathematical modeling, and different perturbation techniques. One of the most important theoretical concepts was put forth by Chu and Kovesne, who decomposed the oscillatory component into 3. The compressible irrotational acoustic wave, UHAC, and this describes the production, propagation, and absorption of pressure waves, whose compression and expansion lead to the onset of acoustic waves. Next, we have the U tilde, which is the incompressible rotational wave, and it captures the production, convection, and dissipation of vorticity fluctuations. And finally, we have the heat-like U brevi, describing the entropy wave that stems from the production, convection, and diffusion of heat. Now, in asymptotic approaches, the methodology is usually set up this way. The instantaneous flow governing the equations is split into 2. The mean flow, which is a steady component, and the unsteady flow, the fluctuations. Then using perturbation expansion, only the first order terms are collected. Then using Helmholtz decomposition, the fluctuation equations are split into 2. The compressible irrotational acoustic wave and the incompressible rotational vertical flow. Now, entropy is ignored for simplicity, and since the vertical set can be solved using normal mode analysis, is again further split into axial and transverse equations. Now, though this process seems extensive, the analytical process serves as a basis for construction of numerical stability frameworks. Acoustic wave is given by the isentropic wave equations. It is second order linear PDE. Here, CW is the speed of sound. And this describes the propagation of oscillations at the speed of sound. In the absence of the mean flow, that is when CW is equal to 0, we can extract the theoretical acoustic frequencies using KL is equal to L pi by L, and here KMN is the transverse wave number and KL is the longitudinal wave number. So just for an example, if we need to have an estimate of the frequencies, we can use KL is equal to L pi A by over the aspect ratio of the motor, and it will give us an approximate value for the longitudinal waves. For instance, if we have a 10-meter long motor, the first frequency will be close to 17.15 hertz. Here we have the acoustic mode shapes of the first, second, and third pressure waves or pressure oscillations. Now, moving on to transverse oscillations, we have tangential and radial oscillations, and these are given by the Jacobians. So for M being the tangential mode number and N being the radial mode number, we'll be able to extract the mode shapes of the tangential modes and the radial modes. And we also have mixed modes where both effects will be observed. Using separation of variables, the wave equation can be solved to obtain the acoustic wave equations, but because the acoustic field is irrotational, the diffusive terms accounting for the boundary layer do not exist. Therefore, it cannot satisfy the no-slip condition along the solid boundaries. Physically, however, as the acoustic velocity interacts with the solid surface, it generates vorticity, which acts as the acoustic boundary layer to bring the unsteady velocity to 0. So by solving this, we'll be able to identify equations for the axial velocity, radial velocity, and also the tangential velocity. Now, the rotational compressible wave serves as a correction to satisfy the no-slip condition. The solid boundaries can be written as given over here. You can see that we are preserving vorticity also over here, and this is for an incompressible wave, obviously. In order to remain consistent with the acoustic solution and motivated by the form of normal mode, the vertical solution, it must take the form with the vertical amplitude, and here we have the velocity multiplied by the exponential of im theta minus omega t. So here, this will give us the expressions for both velocity, all the 3 velocities, and also the pressure. So using the equations from the acoustic waves and the vertical waves, it will allow us to get the solution for the vertico-acoustic wave. So Dr. Marzolani's seminal paper on the oscillatory pipe flow provides an analytical representation of the axial component of the vertico-acoustic wave. Here, F captures a mean flow function. Phi naught, phi1, and zeta are functions of Stroh-Hall number, injection velocity, geometry, wave number, and modal frequency. Thus, they are all describing all the aspects of the flow. By obtaining the time-stripped modulus of the wave, we can understand the nature of the vertico-acoustic wave and also use it to verify any stability framework. Now, this slide here shows the unsteady axial velocity waves for longitudinal mode number 1 and 3 at 4 different increasing Stroh-Hall numbers, 50, 100, 200, and 400. Now, as you can see, the rotational amplitudes reach their peak values as oscillatory pressure nodes. We also observe premature 0 rotational amplitudes caused by especially the 0 unsteady vorticity, which will originate to the velocity nodes. We'll look more about it in detail later. Now, this can be observed clearly in a port plot. So these are the results for mode 1, 2, and 3. For mode 2, we observe 1 premature zeroing downstream and twice in mode 3. And conclusion is that from here is that when analyzing the stability of a long solid rocket motors, these results will come in handy, and it will also allow us to understand the physical mechanisms at play. As you can see, this actually shows us that vorticity originating from the zero velocity line nodes plays a very important role in here. Okay, so since I'm going to be considering the modeling and prediction approach, what should our model be able to do? It should be able to describe both acoustic and vertical waves along with their interactions, should be able to propagate the acoustic waves, describe the details of the internal flow, including capturing vorticity and flow instabilities along with their growth rate, evaluate stability of the motor in the presence of different mean flows, include a current space model, include non-linearity in the model, coupled with combustion models, also coupled with solid mechanics model to model the regression rate in solid rocket motors. So, linear stability analysis. Many flow features of engineering interest occur because of nonlinear interactions. Currently, we have no robust solutions for the 3D Navier-Stokes equation, especially the momentum equation. And there is a $1 million prize from Clay Mathematics Institutes if we prove or disprove it. And mostly the common techniques to achieve approximate solution to nonlinear PDEs is to linearize the equations. That is why we get the linear stability analysis here. Now, though the linear assumption is only valid for small fluctuations, it is still useful for detecting physical growth mechanisms and identifying dominant disturbance types. So our analysis is restricted to the linear solution, but it serves as a precursor for the nonlinear analysis. As graphically shown here, the intrinsic instabilities of mean flow generated by the combustion of the propellant grain has been identified as the primary source of pressure fluctuations. These fluctuations propagate to the medium and join with the global unsteady field in the chamber. In a closed boundary condition, the pressure wave gets reflected, mimicking a feedback amplifier. Now, the coherent structures that are formed might grow to large amplitudes, and they are what are expected to induce a transition to turbulence. With linear stability analysis, we can predict if a system is stable or unstable, where the oscillations are purely sinusoidal and are low in amplitude. Here is a basis for linear stability analysis. We have the governing equations as an initial value problem. After linearization, we decompose the flow quantities into mean and perturbations, and then drop the higher order terms since they make the flow nonlinear. Now, linear assumption only says what happens when the disturbance amplitude is small. So nonlinear effects are definitely need to be accounted for. In linear stability analysis, there are two types based on the solution approach. We have the modal analysis, which approaches it as an eigenvalue problem, and they are further divided into local and global techniques depending on the dimension of the mean flow. Non-modal analysis approaches it as an initial value problem and detects the transient growths in the flow. We also have spatial and temporal stability analyses. Spatial stability analysis are generally preferred by experimentalists to more easily identify perturbation characteristic for single frequency waves. Here in a spatial stability analysis, we constrain omega to be a real number. Physically, this means that we force a sinusoidal perturbation at a particular point in space and see if they grow or decay, which will be given by the sign of the wave number alpha I. Spatial stability analysis are more difficult to perform than temporal stability analysis, and if the flow is absolutely unstable, they will have no physical relevance. Why are they more difficult to perform? Because the resulting matrices are 4 times bigger than the temporal linear problem. And the first attempt to study the relation between spatial and temporal instabilities was made by Gaster. And for the problem that we currently have, it is significant that we use a temporal stability analysis. The non-modal approach developed in the 1980s, and it takes into account the non-normality of our eigenfunctions and the properties of the whole spectrum of eigenvalues. So the figure here, it shows non-modal linear stability analysis of Poisson flow through a channel. Here, alpha and beta are wave numbers in the x and y dimension. The maximum transient growth rate is that alpha is equal to 0 and beta is equal to 4, as indicated by this black dot over here. And Ghosh and his team, they postulate that to reduce more information about the onset of linear instability, we also need to consider the modal approach. And here, the non-modal stability approach is very useful for uncovering flow properties like short-term dynamics or transient amplifications, as a modal approach actually cannot do that. Moving on to modal approach, let's look at the modal decomposition of two-dimensional incompressible flow over a flat plate, a Reynolds number of about 100 and an angle of attack of about 30. Here, we clearly observe the formation of von Karman vortex sheet in the wake as the dominant unsteady feature visualized by the streamwise velocity profiles over here. Back to the study of Poisson flow through channel by Ghosh, modal stability analysis shows contour plot of the growth rate of the least stable mode in the alpha beta plane. Here, the blue line, it represents the contour growth rate of about is equal to 0. Here, the figure below. Oh, yes. And Ghosh and his team concluded that the instability mechanism at play here is the Tolmie-Schlichting instability after looking at both modal and non-modal approaches. The figure below shows the dynamic mode decomposition of a jet in cross flow, with each having different characteristic frequency of oscillation, and this was possible only through the modal approach. Here, the three snapshots over here shows 3 different frequencies, and you can observe how different they look depending on the frequency. That is why modal approach plays important role in especially the rocket stability analyses. Now, how are modal and non-modal instability analyses mathematically different? To reiterate, modal stability analysis is an eigenvalue problem, and to find the unstable modes and the non-modal and the non-modal stability analysis is an initial value problem where we solve using singular value decomposition or matrix factorization techniques, and that is used to determine the maximum transient growth rate. For fundamental flow problems such as flow over a flat plate, liquid flow, etc., researchers perform both types of stability analysis to understand all the mechanisms at play. But when we have complex flows, it's better to, since it is computationally costly, we choose which is more convenient to us and which gives us the results that we desire. So for the combustion instability problems based on the superposition of eigensolutions, instead of just analyzing the eigenvalues, non-modal analysis is always more computationally expensive. Modal stability analysis would fail to capture the transient or non-modal growths regardless if the flow is asymptotically stable or unstable. So with our research, we conclude that ultimately the choice between modal and versus non-modal stability approach is motivated by which framework better matches reality for a given study. And we concluded that we'll use the modal stability approach. Types of linear stability analysis depending on the nature of the base flow. So we have local stability analysis for parallel flows and the global stability analysis for 2-dimensional and 3-dimensional flows. Let's look at the problem setup and how it is usually done. Real flows are generally 3D. So we have spatial homogeneity assumptions framed in either modal or non-modal approach, and they greatly simplify stability analysis. For the 3D base flow and perturbation, the linear Navier-Stokes equations, we have the continuity and the momentum equation with viscous dissipation and the convection term, along with the pressure source term, which captures the flow physics very well. For a parallel flow, the mean flow depends on a single space coordinate here, the y. Now, the linear dynamical system now becomes autonomous in time and in the x and z coordinates of space. So the perturbation Q can be decomposed into normal modes given by the local ansatz, Q of y exponential of I alpha x plus I beta z plus omega t. Here, alpha and beta are the wave numbers in the streamwise and spanwise directions, and omega is a complex number with the real component giving us the frequency of the oscillations, and omega I giving us the temporal growth rate. Taking the divergence of the momentum equation and eliminating the pressure in equations, applying the local stability analysis for perturbations, which we saw in the previous slide, setting up it as an eigenvalue problem, it gives us and solving it gives us the Orr-Sommerfeld equation, where alpha is the wave number, d is the second order derivative, and omega is a complex frequency, and psi is a stream function. So applying this Orr-Sommerfeld equation to any problem or a fundamental problem with parallel flow assumptions will give us the stability analysis for the particular problem. Now, local instability techniques are quick and they work surprisingly well, but are not strictly valid for flows that evolve rapidly in the streamwise direction. So, Orr-Sommerfeld analysis of the plane Poisson flow with the isocontours of growth rate is given over here. Here, as you can see, the neutral curve begins over here, which gives us the critical Reynolds number for the onset of the instability at about 5773, marked by the vertical broken line over here. Now, this local stability analysis, it analyzes only a portion of the entire flow to determine the stability and then extrapolates to the entire flow. And this is commonly used for boundary layer transition analysis. It is valid only for parallel flows to reiterate where the flow does not evolve rapidly in the streamwise direction. Now, when we are looking at local linear stability prediction analysis, the stability of the base flow is governed by the growth rate omega I. If omega is less than 0, this means that the mean flow is locally stable. If it's greater than 0, it's locally unstable. So for a stable flow, we need all the omega i's to fall below the 0 line. From a theoretical point of view, it relies heavily on the parallel flow assumptions, but it provides insights into the local stability of the flow, and also it requires a good theoretical mathematical background to understand what exactly is going on in there from the figures observed. Practically, the generalized eigenvalue problem involves smaller matrices, which lowers the computational cost, and it can be solved using direct solvers in a matter of seconds, even in a decade-old laptop. Moving on to non-local stability analysis. Here, we relax the parallel flow assumptions and extend it to weakly 2D flows. Here, it accounts for local conditions and also the upstream conditions, and it's very useful for evaluating boundary layer growth. The figure over here, it gives skin friction coefficient versus the Reynolds number. As you can see, the lower minimum and the steeper rise of CF here, the experimental results are given by these squares, and the stability analysis is given, non-local stability analysis is given by the lines. This is of the ECOFTAC T3A flat plate test case. We can also see, and this is captured by the parabolized stability technique. So when we are considering the weakly 2D flows called the non-local stability analysis, it's the equations are termed as parabolized stability equations, and this was done by Herbert and researchers. We can also see that when the accuracy increases with the high grid resolution. Now, the parabolic stability equations are actually solved as an initial value problem through marching procedure along this downstream direction. Using the resulting complex streamwise omega, the wave number alpha r, and the amplification rate alpha I, which is determined at each successive step, we'll be able to know about how the dynamical system works or how the stability is there. Okay, moving on to biglobal stability analysis. Here, the paradigm shifts from local to global. Global meaning that accounting for the entire flow field at once. It is a 3D analysis, but we assume that perturbations in the streamwise directions are periodic, and it is useful for analyzing cylinder, step, or open cavity flows. So how it is set up, we have the continuity, momentum, and energy equations with the terms in blue denoting the convection, the terms in orange denote the viscous dissipation and conduction, and the terms in red are the source and forcing terms. Here, it's generally the pressure. Now, before moving further, it may be helpful to recognize that our problem comprises of two activities that evolve over two dissimilar time scales. The mean flow transients, which unfold over the regular time, and the oscillatory motions, which evolve over a faster time scale, which denotes the oscillatory frequency of a given disturbance. In dimensionless form, this two timing behavior, it actually enables us to decompose all the flow variables into mean components and the first order disturbances. Second order perturbations make the equations non-linear, as I mentioned before, so only the first order terms are included for the linear stability analysis. Now, by collecting the terms, two sets of equations emerge here. The first is the non-linear steady set describing the mean flow field. Because solutions of the base flow are available in a complex compressible context, there is no need to solve this non-linear set. Instead, the analysis is only focused on the first order unsteady equations. So generally, when using Helmholtz decomposition, it needs to be resolved into the three components as stated by Chu and Kovesny. But when you include compressibility in the equations, we can get all the modes in one shot. That is the main that forms the main crux of my research, actually. So for our analysis, we attempt to investigate an axially symmetric flow, considering the theta direction to be homogeneous. The fluctuating component can now be expressed as a function of its 2D ansatz as the amplitude multiplied by the exponential of I m theta minus omega t, where omega r is the frequency and omega I gives us the growth rate. Now, this biglobal ansatz for each unsteady variable may be inserted into the linearized form of the principal equations, and setting it up will give us the compressible biglobal equations. Moving on to triglobal stability analysis, for the more generalized case, the flow is treated as fully 3D, inhomogeneous in all three spatial directions. No spatial assumptions are made, and they are ideal for highly 3D flows. But why is this approach not always used? It because it takes large computational time and a lot of space is required, and it is sensitive to preconditioning. On the right, we have the biglobal and triglobal velocity comparison of the most unstable mode in a lid-driven cavity flow published by Barthes. As you can see, biglobal stability analysis does provide a good approximation of a 3D flow, but to identify how the structures actually look, it's better to use a 3D setup or a triglobal stability analysis. So in summary, here we have for global techniques, we have the triglobal, PSE 3D, and biglobal approaches with how the basic state looks, followed by the perturbation, and non-local, which are solved using the parabolized stability equations, and local or Sommerfeld equation, where, as you can see, the basic state is only one-dimensional. Now, the Taylor-Kulik mean flow field. The cosine-shaped Taylor-Kulik velocity profile, it precisely captures the flow in a solid rocket motor. So when we are dealing with solid rocket motors, we tend to use, all researchers tend to use the Taylor-Kulik profile. In his paper, Sir Geoffrey Taylor explains how this novel profile started out as a means for solving a practical paper industry problem, like all research ideas do. He developed the analytical solution for the flow through a porous tube and verified it experimentally using this setup in the Cambridge Engineering Laboratory. Here, so this is the porous tube with just a water tank to collect the water. So this animation shows the axial velocity profile of the mean flow. The preceding profile in red is the compressible electrolytic profile, and the following curve is the incompressible one. The compressibility effects become observable at about 40% of the length of the chamber and about halfway between the center line and the wall. We observe the steepening or what we call as a flow turning, which causes the entropy fluctuations. And here, the figures below, the solid lines denote the incompressible and the dashes denote the compressible solutions. In shorter chambers, when the aspect ratio is less than 10, they don't have huge discrepancies. But in the case of solid rocket SLS rocket boosters, which are longer with higher aspect ratios, compressibility effects become very pronounced. Why include compressibility effects? Compressibility is a key parameter in capturing acoustic waves because that is how they propagate. Entropy fluctuations are significantly affected by compressibility, and when we are adding combustion models to the stability analysis, compressibility is required, and also to capture the coupling between acoustic and vertical waves, also to be used with compressible mean flow profiles. And when we need to validate the solver with existing experimental data, compressibility is required. That is why including the compressibility when designing the flow field became a very important thing in my research. So the quest for a compressible mean flow expression serves multiple objectives. First, it was needed to improve our representation of the undisturbed inviscid field and its impact on the acoustic wave motion and also the flame zone analysis. It provides a more consistent solution for the total internal flow field by insisting that both mean and unsteady component retain a compressible ingredient. Most of the analysis, they consider that even though they consider that both the mean and the unsteady component to be incompressible, that is where the discrepancy happens. So what happens is this has upgraded our analysis to hydrodynamic instability, which so far has been limited to incompressible equations. As you can see, this retains the cosine shaped axial velocity profile, and similar radial velocity profile expressions with compressibility corrections. This was given by Dr. Marjolani's 2007 paper, and it is a closed form solution. So in addition to the velocities, we also have readily available expressions for density, pressure, and temperature. So this negates the need to find the mean flow solution, and it saves us time, and it also provides a quick start for the solver. Looking at other mean flow profiles, the introduction of swirl often leads to innovative design concepts, higher efficiency and performance, self-cooling capability, and many more advantages in propulsion industrial applications. So in comparison with the Taylor Curie formulation, where the tangential motion is generally suppressed, the angular momentum associated with the Tilchallen model is granted the freedom to change with the stream function, which characterize the helical flows generally in spinning rocket motors. Similarly, bidirectional flows in cyclone separators and reverse vortex chambers are of interest due to the novel bidirectional vortex engine from the Advanced Propulsion Research Laboratory. So studying the stability of the vortex engine using the complex lamellar mean flow and the Beltrami class of mean flows are of significance here. So building a stability framework that can work with readily available mean flow solutions will definitely benefit the aerospace community. And that is one of the major goals of my research. Now, looking at the numerical methodology, we have continuous and discrete approaches. Continuous approach where the Navier-Stokes equations are linearized and then discretized. Discrete approach where the Navier-Stokes equations are discretized and then linearized. So we use the continuous approach here. And discretization is generally done through spectral methods, finite difference methods, finite volume methods, and finite element methods. And how are the discretized equations solved? We have matrix forming methods, direct methods, which uses the QZ algorithm, which returns a full eigenspectrum, and the iterative methods, which gives results only after a few iterations, using the Arnoldi process. Now, flexible approach. Now, this we use spectral methods in here after deliberation because of a variety of reasons. Since we have oscillatory waves evolving in 2 different time scales and multiple length scales because of the presence of coherent structures, spectral methods turn out to be the best option. However, spectral methods can be less practical in irregular geometries or where strong discontinuities may be present. Spectral methods taken over a non-complex circular geometry are very accurate, even when taken over relatively coarse grids. Wave propagation problems, they require both high spatial and temporal resolutions. And in aerospace applications where we have very high Reynolds numbers, they require a numerical method with optimal resolution power for a given number of discretization points. Theophilus, he postulated that to recover the same level of accuracy through a finite difference scheme or a mixed scheme, 4 times the number of grid points that in a spectral discretization is required with almost the equal amount of time with the same CPU workload. So spectral discretization makes our job easier. Now, finite difference is a local method. Spectral methods are global methods where the computation at any given point depends not only on the information neighboring points, but also on information from the entire domain. Spectral methods generally converge exponentially, which makes them more accurate than the local methods. Global methods are preferred local methods where the solution varies considerably in time or space, when very high spatial resolution is required, and also when long-time integration is needed. So let's consider a simple partial differential equation where L is a linear operator. Lu is equal to f of x. How is this solved numerically? We approximate the unknown u using a sum of basis functions phi n, and here we have to choose a series of coefficients an such that the residual tends to 0. Now, here we need to choose, make a choice for this an and phi n in here. How to choose the approximating on the basis function. Now, the test functions are a family of functions to define the smallness of the residual R. So we have the Galerkin method, tau method, and the collocation method. In the Galerkin approach, the residual of the approximating function needs to be orthogonal to the basis functions. For the present problem with 6 unknowns, inner products can become very laborious and may even diminish the possibility of successful outcome. For tau method, the approximating function needs an additional set of equations for the boundary condition. Collocation method, which are also called as a pseudo-spectral methods, because we take the derivative, and because the residual of the approximation function vanishes at the collocation point, the derivative is essentially rendered exact at this point. Now, so we choose collocation method in here for a problem. Now we want the basis function to be easy to compute, converge rapidly, and also provide completeness. Completeness meaning that any solution can be represented to arbitrarily high accuracy by taking the truncation n to be sufficiently large from over here. So we have 3 options here. We have the Fourier series, but it might have difficulty with the Gibbs phenomena, where there is an overshoot of Fourier series and other eigenfunction series occurring at simple discontinuities. Next, we have the Legendre polynomial, which may be subject to the Runge phenomenon. And because of the oscillations at the edges of the interval that occurs when using polynomial interpolations. We have the Chebyshev polynomial, and it suits stability analysis perfectly. And why is that? So when we're considering this Chebyshev polynomial, a semicircle is drawn over our interval centered at the midpoint, and the semicircle is split into n arcs of equal length, and the arcs are projected onto the x-axis. So as you can see, the blue ones are the equispace points, and when they projected, they give the Chebyshev nodes, which are denoted by the red dots over here. So as you can see, when it's translated onto a cylindrical grid, like we wanted the Chebyshev nodes, it gives us more resolution at the boundaries, which will help us to capture the coherent structures arising from the parietal vortex shedding from the walls. So Chebyshev polynomial works the best for a stability analysis or of a flow. Okay, we call it the generalized eigenvalue problem because a single matrix problem would be an identity matrix over here. Now, the set of PDEs from our equations will, when we set it up as eigenvalue problem, with lambda is the eigenvalue, Fi is the eigenvector, and Aij and Bij are the operator matrices. Now, each operator matrix can be conveniently subdivided into sets containing the coefficients of 5 dependent variables and 5 equations. So we have five different variables. So each subset compasses the multipliers at every grid point for n by n colligation points. The operator matrices Aij and Bij would consist about 25 n to the power of 4. Yes, the matrices are going to be huge. So to provide a graphical representation, as you can see, we have 5 variables: axial velocity, radial velocity, tangential velocity, density, and temperature or pressure, depending on what is comfortable when we're working with stability, and 5 equations: continuity, z momentum, r momentum, theta momentum, and energy equations. And we have 2 operator matrices, Aij and Bij. So after setting it up as an eigenvalue problem, we can solve it to get lambda. And as I explained before, we have 2 different types of approaches to solve the eigenvalue problem. We have the direct method, which is the Arnoldi process, and direct method is the QZ process, and the iterative method, which is the Arnoldi process. So Arnoldi is generally designed for sparse matrices, and it requires less hardware capabilities, and it computes specified range and shorter run times. But when we are dealing with a completely new rocket design, we definitely will not know where the problem might arise. So it is imperative that we compute all the eigenvalues at once. So it is necessary that we use a QZ algorithm. But if we already know where the instability is going to occur, we can always use the Arnoldi process by giving a quick start for the solver. The global linear stability analysis, it requires high computing efforts and the core memory storage space required for the d spatial directions and n spatial discretization points. It can be calculated using the formula, empirical formula given here by Theophilus. He enumerates through experience that for a one-dimensional problem, n is equal to 64 is adequate to capture the eigenmodes in bound layer flows. From my previous researches, I have observed that even for two-dimensional flow like ours, 60 or 70 works best, and I generally tend to use n by m, where 120 along the streamwise direction and 60 or 80 along the spanwise direction. Some of the milestones in stability analysis, everything started with Navier and Stokes, motion of the viscous fluids, and followed by the Reynolds pipe flow experiment in 1883, where Reynolds developed the Reynolds number, which distinguishes stable and unstable flows. Next is the Rayleigh inflection point criterion in 1887, and Sommerfeld viscous equations for the one-dimensional flow. Heisenberg, Tolman, and Schlichting viscous solutions, and they played a very important role in characterizing the instabilities based on how they look, and the square theorem, 1933, Stuber and Skramstad gave the experimental verification for viscous solutions specifically. And the Arnoldi additive process algorithm was put forth in 1951. Gaster came out with the spatial stability theory in 1965. Joseph formulated the maximum energy growth technique in 1976. The first global linear instability study was done in 1982. So it's not, it's a recent technique, I would say. Hall solved the parabolic equations for boundary layer disturbances in 1983, but the parabolized stability equations, the pioneer is Herbert and his team. And the non-modal analysis technique was developed in 1992. Given the computational cost, the reduced order modeling for biglobal instability was done in 1944. The PSE 3D approach for, let's say, weekly 2D flows was done in 2004. The first triglobal analysis was done in 2006. High resolution CFD analysis was done in 2011. Along to analyze the thermoacoustic instabilities. So when we are dealing with cold flow, we call them vorticoacoustic instabilities, but when combustion comes into play, they become thermoacoustic instabilities. Was done by Grossi and his team in using the quasi 1D model. The nonlinear thermoacoustic instabilities was analyzed by Cecil from our very own Advanced Propulsion Research Laboratory, and the triglobal stability analysis of the thermoacoustic field rocket engines was done by Koesik, both in 2020. And recently, Grossi and his team, they came out with an upgraded Q&D model with thermoacoustic and hydrodynamic resonance. So these are some of the milestones in stability analysis. So to summarize everything, for combustion instability applications, unstable behavior is linked to both acoustic oscillations and hydrodynamic vortex shedding. The goal of a combustion instability analysis is to obtain the first few resonant acoustic modes of the configuration for any given mean flow profile, like the Taylor-Cubic mean flow profile for spinning rocket motors, and the bidirectional motions with using the complex laminar and the Beltramian class of equations. So when designing our one swoop vorticoacoustic and hydrodynamic solver, first we take the governing equations, continuity, momentum, energy, and the gas law, linearize the equation, and then perturb it, giving us a mean flow component and an oscillatory component. Apply the mean flow that we want, that we are looking for, and apply the biglobal stability ansatz for our oscillatory equations. Set up everything as an eigenvalue problem and solve it using MATLAB. And that gives us a frequency spectrum. More about how to analyze it more in my next video. Now, results from the analytical solutions for acoustic mode shapes for longitudinal, radial, and tangential waves, they can be employed for verification. For instance, this is suppressing the mean flow, setting that just the Mach number is equal to 0 will give us the mode shapes for the longitudinal modes and the radial mode. So this is for the first longitudinal mode and the first radial mode over here, thus verifying the solver. Again, to reiterate, experimental results from Waldo cold flow setup can be used to validate solver. So recreating the same flow conditions from Waldo, and our solver should be able to identify the 3 distinct peaks at 170 Hertz, 320 Hertz, and 500 Hertz. So these are some of the references that I used for my literature survey. And that concludes my presentation. So to infinity and beyond, but also safer. Thank you.